Okay, we're going to go ahead and get started. In this session, you're going to see a diversity of things being described. We're going to go over the new RFPs coming out here from NASA and delve into topics around microfluidics. And then STEM is always a very important area for us, and we're going to hear a little bit about that. And I think that last talk will also reflect a desire to reach out beyond protein crystals as well. So with that, Craig is going to kick us off here. No. Right. Oh, there it is.
Okay, thank you. Okay, you said. All right, so good afternoon. It's great to be back with this crowd, my old research area. This is a great talk to transition us from the morning session and capabilities into like the next talk about cases and future plans. This is more of a programmatic talk, although if we want to get into a little of the technical, we can try and dive into that. As you well know, there are significant deviations in practice when we talk about doing crystallizations in space. And this has been true since the first days of the shuttle, but it carried over to how we use the space station, first serviced by shuttle, now by Dragon. And in future, as we have the Boeing Starliner and the Sierra Nevada Dream Chaser, if we don't do anything differently, we'll face the same kind of challenges. So to pick some of the top level ones, we'll look at timing between events in the terrestrial realm and what we do in spaceflight practice, currently or over the years. So first, purifying one's macromolecule and setting up crystallizations. For many systems, you really need to be crystallizing fresh material. And with all the logistics associated with spaceflight, that's not a viable proposition. And today, I don't have a solution for you on that front, although we'll talk about a modification of that limitation. But the next three, we think we can improve on. Crystallization setup and start of equilibration. For your typical vapor diffusion experiment for spaceflight, the initial conditions are established on the ground, and something is done to arrest equilibration. It could be freezing the solutions, could be putting in a barrier, like in the case of PCAM or HDPCG. And those work, but those are not things you do in the terrestrial lab. And so a lot of systems are not, don't really perform well after that kind of treatment. There could be a really long delay between the crystal growth being complete and the ability to inspect what you have and or harvest it. So in the lab, you may be setting up 2 or 3 rounds of crystallization trials a week and harvesting them after you learn how long it takes your crystals to grow, basically right away. Whereas in the case of the spaceflight program, especially with launch delays, which may delay your return ride, et cetera, you might be waiting many months and your crystals degrading. We saw examples of that this morning. And then lastly, this whole notion of iterating. We know how empirical crystallization is, and our typical mode is you fly one set of conditions up and have to wait for those to come down before you iterate. Whereas in the lab, you're looking at your results, and usually that same day, setting up your next round of crystallization. Well, we just learned to live with this, and our eyes were kind of opened anew when Kate Rubins flew in 2016, a card-carrying molecular biologist who gained a lot of fame, as it were, for sequencing DNA for the first time in space using the Oxford MinION. But in her spare time, being a good geek, she used some of her elective time to, as was mentioned earlier this morning by April, she brought up some extra pipette tips and tubes, and long and short of it is, she found that pipetting into Eppendorf's, Falcon tubes, 15 mil or 50, tissue culture trays, 24 well, 96, whatever, that was all very doable. One has to take care to do things slowly and deliberately, but all the unit operations in molecular biology are doable. And it doesn't take fancy technology. I think the fanciest addition of technology was the use of duct tape in the open area just to keep tubes from floating off into space. Okay, so interestingly, you can just take a 50 mil tube and just push it against the tape, like on the work surface, and it just sort of sways there a little bit, with the air currents, but it stays in place. So that inspired us and triggered some old neurons. Back, Eddie will remember this, when we were at Marshall and working on a project called Iterative Biological Crystallization. So this is out of the Kundrot archive, clothing archive. This is a shirt from those days, that project, where we sought to use robotics in space to do crystallizations on station, feed into Larry DeLucas and UAB's team's capability for X-ray diffraction and crystal harvesting. And so it's basically the same mindset, but that program was, for various high-level reasons at NASA, basically truncated. So those old neurons have fired again, and instead of using the robotics, we'll use the human, because right now as we speak, we have 4 U.S. operating segment crew members on station available to do work, and so crew time is plentiful. Now we're going to go back into a valley where we're not going to have 4 crew members. We'll be back to 3 for hopefully just a year or so, or maybe less, waiting for a commercial crew to bring us back to 4 crew members. So that's either from Boeing or SpaceX. But we expect to have a lot of crew time available again in that era. So the idea is, let's use the human, and basically as a graduate student, postdoc, technician, whatever, on station, conduct the crystallization trials in the way that we're accustomed to. So we'll send up stock solutions of the crystallization target of interest and the reagents needed for the crystallization recipes. Have the astronauts iterate. So they'll set up crystallizations, view them under the microscope, beam those down to the PI on the ground, and then get instructions for the next set of recipes to set up. And then, along with that, as we gain familiarity with how long it takes that particular crystal to grow on orbit, we will time the last crystal growth such that on the return ride, we'll be returning fresh crystals, not something that is weeks or months old. So with this kind of approach, we modify this first limitation a little bit. There's still some systems that will not be amenable to this approach, but we have to have macromolecules that can be crystallized from stored aliquots with not a lot of extra processing. So either frozen or held at 4 degrees probably. Maybe the best we can do is centricon them just prior to use. Then on the other 3 areas, we should be able to severely reduce these delays. So in actually setting up the crystallizations on orbit, that should mimic very closely what we do on the ground. When it comes time to look at the crystals, we won't be harvesting in space, that's present. But when it comes to inspecting them, that delay will go down from weeks or months down to days or weeks. The one thing about our crew is they're very busy. They are human subjects in human subject research for about a dozen investigations typically. They're also conducting physical science experiments, other things. They're keeping the vehicle operating. So we cannot expect their response to these experiments to be the same as graduate students in our laboratories, at least not yet. But still, it'll be hopefully a dramatic improvement there. And then also the time delay between inspecting the results of one set of trials and setting up the next should similarly be reduced. So to do this, we're calling this effort real-time protein crystal growth. It's very similar to the in situ protein crystal growth effort you heard about this morning. The plan of attack is to look at readily available hardware that's particularly flown before or easily certified. And so entering into this effort, the 3 leading candidates were Robbins plate, PCAM, and DCAM. And DCAM is not listed here in preference to enhanced DCAM. That was just sort of a simplification. And the idea is for any particular hardware done in this project, we'd go through 3 phases. First is developing crystallization procedures and observation techniques for that hardware using test solutions. So this is primarily just from a safety and toxicity perspective that we can do this in the open air on station. Second, move to the same development of methods using a model system, basically a positive control, like lysozyme or something else. So now you're actually testing for like the ability to observe crystals in the system. And then lastly, in phase 3, move to targets of actual research interest. And that would then be followed up with terrestrially with X-ray fraction studies. This says RTPCG2 because phase 1, RTPC1, we enlisted the help of Larry DeLucas, who had an active grant. So we expanded the scope and got some solutions up there, materials, crew time, to test things out. And earlier this morning, I misspoke. Turns out the PEG solution that he found to have trouble mixing, or the astronaut did, was PEG 6000. So not such a high molecular weight. 600, PEG 600 was fine, but 6000 was a little bit more problematic. So in RTPCG2, the plan is to bring in, and what we have done, is bring in a brain trust to help us. So in our division at headquarters, Space Life and Physical Sciences, we emphasize, as much as we can, open science. And open science really has 2 components. Up front in an investigation, enlisting a team where that makes sense. Our best success in that area is the twin study, where we brought in 10 investigators, which was really bringing in 10 teams, to look at everything from epigenetics to cognition for the Kelly twins in that study. In this case, we released an RFI, and this is all in conjunction with cases. I should have said that at the very beginning, that we coordinated upfront with cases, the idea being SLPSRA, NASA, will work on the methodology and set that up for cases to then use in their program as an offering. So we released an RFI to solicit members for a science definition team. The other part of open science is, after an investigation is done, making the results, the data and results readily available to the community for follow-on analysis or whatever. So the project team that we have is led by Marshall, Space Flight Center. Ben Penn is the project scientist and Sean Reagan the manager. And then our science definition team includes 3 members here today, Dan, Tim, and Eddie. And then Larry DeLucas and Stephen Quirk are other members of this team. So they are the brain trust that is guiding this effort. Their tasks are to advise on the selection of hardware, and we'll start with one, but we'll see how this goes. We might do multiple types of hardware. Advise the team on the choice of test solutions and model systems, and eventually the novel crystallization targets. And along with that, develop and refine the procedures for the crystallization setups and the observation. Now, as a real-world test and as a reward to the science definition team members, they are encouraged to, but not required to, provide real-world crystallization targets and the attendant reagents for crystallization in space, and do the subsequent analysis on the ground. So the idea here is to cast the net broadly, and with this group, so my apologies to Dan, Eddie, and Tim. I'm painting a target on you right now. If you have ideas for how this use of space station and real-time protein crystal growth could be improved, I encourage you to talk to them, because they're the mental funnel that is guiding this effort at NASA. So to conclude, deviations from standard terrestrial practice limits the value of crystallization on orbit. The real-time protein crystal growth project is seeking to remove some of those limitations and increase the success rate of crystallizations in space and the throughput It's a collaboration with Slipsra and CASIS, where we are working hard on the methodology on the upfront part, and CASIS providing the resources and the follow-on work. We're engaging the research community through the science definition team, and follow-on work past RT-PCG will be part of the CASIS program. And so that's real-time protein crystal growth at NASA.
That's great. Okay, Mark's going to talk to us about the proposal request from CASIS and relate it to what we just saw.
Yep. So did everybody get the postcard that was at the front table for the RFP? Okay. So there's a postcard at the front table, the RFP details.
Yeah. Oh, there it is. Yeah.
Okay. All right. So I will start with a little introduction of who CASIS is. So we get confused a lot for NASA or the people that are in charge of everything that goes on in the world of space research to the people that prevent anything that goes on in space research. So CASIS is an acronym for the Center for the Advancement of Science in Space and emphasis on science. We are actually a nonprofit company, but we have a collaborative agreement through NASA to be the managers of the Space Station National Lab. So what that means is that we have a dedicated mission to utilize that resource for Earth-based benefits. So through NASA, we have access to some of the resources, about 50% of the resources on the launch, as well as on facility, as well as the crew time. So that's a close relationship that we have with NASA in that. And we're charged with working with a diverse array of people from the implementation partner community who you've heard of, to the researchers and to other government agencies and commercial companies to try and maximize the utilization of the National Lab. So why space? I think that is the question that always gets asked. And I think that the audience here and the presenters have done a good job at least explaining the microgravity environment and what it can do for protein crystals. And you'll see that I'm going to try to expand that outside of just the area of protein. And, you know, obviously I get to show these slides because they're really cool. But I'm going to show these other two areas that we often talk about. So the facilities outside the station where you can do some material testing utilizing extreme environments that are outside the station, as well as the ISS National Lab provides an opportunity, but a unique vantage point to look back at the Earth or look out into space. And so I bring these up as well because our mission is solely focused on utilizing that national lab for the benefit of life here on Earth. But as much as this community would probably like us to focus on the microgravity component and specifically on doing protein crystallization with that microgravity component, we have a much broader mission, and we have to try to facilitate the use of all of the features of the National Lab. So we are not necessarily a funding agency. We do through our collaborative agreement have funds that we can provide, but we're more in the charge with trying to generate either other people wanting to put money into research that you all are doing, or commercial companies seeing the value in it, or academic labs seeing that this is a valuable national resource and they'd like to utilize it right now with the subsidies that are provided through NASA and the US government. So specifically, when CASIS began, one of the things that came out of all the previous work that had been shown before, especially from the shuttle era, was that there seemed to be a benefit for doing crystallization on space. And obviously April talked about this, and you've heard a lot of the work that's been done through this RFP. But that was one of our very first RFPs that we put out. And as April discussed, there were 5 PIs selected through this RFP, and we funded the research all the way from the prep to flight, including the flight, the implementation partner side of it, the whole length and duration of those projects. And then from that, we continue to get proposals that came in through cases wanting to utilize the space station for a variety of crystallization experiments, including from Merck, which you've heard, and Eli Lilly. So there continued to be a lot of interest. So we, in 2015, brought together the community, and you've heard a couple people talk about this workshop. And we got some action items coming out of that workshop, including how we can continue to foster this community. And one of the things that we heard the community wanting was us to set standard capabilities from the implementation partner, get them in place, get some fixed costs, get some capabilities that were available that a customer could walk in, they could have them available, we could turn around and get it up onto station. So taking those actions, and I will say that we've heard lots of other suggestions, and we're trying to implement as many of those as we can, but this was one of the ones that we're focusing on today. So from that, we put out an RFP soliciting support services proposals and then issuing contracts from those. And so you've heard from those implementation providers. So they have a suite of options that are available for implementing crystallization projects. And so to in the year since that, we've had a number of proposals come in and been able to utilize this to some degree. But at this time, what we're looking to do with this new RFP that we issued starting today is to further expand the users in that. So we're going to make a concerted effort to try and advertise this as much as we can and get customers to look at this RFP and to respond to this RFP. You'll notice that we've changed it from protein crystal growth to microgravity molecular crystallization growth with the thought that we wanted to expand it beyond just proteins. I think that there's some interest in small molecules perhaps, or other types of materials that could utilize very similar setups. This is the landing page for the solicitation, and again, these slides are all on the website, and there's a postcard with this landing page. So the way that the solicitation we see working is it's going to be a 2-step process, where the first step is that a potential proposer can just submit a 2-page overview of who they are, what they envision for doing in microgravity, and a little bit, so you'll see when you download the 2-page step 1 preliminary review, they're asking for as much details as they can provide as what they envision they would do in space. Those forms will then go to the 4 companies that are part of our implementation partner community, and they'll respond with how they will implement that, and that will go to the PIs, and the PIs will look at that. They can communicate with implementation partners as much as they need to. They'll then select one that's appropriate and work with them to develop a full proposal. And depending on the robustness of this response, which we're hoping is going to be large, we will potentially go back to this community for the people that are not interested in applying for this to ask you to be the scientific review community. So if you're interested in that component, definitely let us know, as we'll most likely do an NIH-style review of the proposals. And then the awards will likely happen in November. So the thought is to Craig's point earlier about what the executive branch feels about the station is that there's right now the language is a transition from a fully subsidized government facility to something that has a commercial slant to it. I think that this community can drive this aspect of the station staying on, and as at least in part subsidized by the government, by showing that there's some value to it, both in an academic sense, but in a commercial sense, or that there's users that are interested in doing that. So that's what we're looking for. And so part of that is that the implementation partner costs for this proposal will still be fully funded, but similar to Craig's real-time PCG, we'll be asking the proposers to provide their own funding for whatever they need to do prior to the work as well as post work. And we've seen a number of cases users be open to this model, especially for this area of research. I think the challenge is going to be from the academic labs, and so I think we're interested in hearing from the community how to support and continue to support the academic labs that may want to utilize an RFP like this. But I think our goal is that if this is a model that works, that we'll continually have an open RFP of this kind. We're looking for feedback from the community if we need to expand and include more services that are not currently available, and we can look into that option. And so how we're looking to promote it is again, we'll do our usual blast through our network of users. Ken and myself will be up at the ACA, and we now have a microgravity session there, and we'll be attending all of the sessions to try and drum up some more support. But the implementation partner community is obviously free to advertise it as much as they'd like. And so the big question is will the customers like this model, and will they eventually move to a model where they're paying the implementation partner? So that's the question that we asked at CASIS. Is this a national resource that people see value in? I know that if Andre opens up and says you can have as much neutron beam time as you want, just bring your supplies, people will run to do that. If we're providing access to the national lab, is it a resource that people will run to and bring their supplies to? So that's the question that we're asking. I think that we're excited about the science that comes out of it, and that's still the main component of it, but we also have to examine if there's a long-term commercial viability for this as well. And I think we're on to...
Next up, Sarah's going to talk to us about some microfluidics.
All right. Yeah, thanks for the invitation to come. I feel a little bit weird talking in this session because I haven't ever sent anything to space, and my expertise is really working on the microfluidics scale, which you could argue could give an equivalent environment to what you can get in microgravity. So a lot of the research in my lab is focused on growing crystals in a microfluidic device, doing in situ diffraction to solve structures, and really to address challenging issues that are more than just everyday structure determination. So when you think about microfluidics, this is probably not true of this audience, but most people only think about it from a volumetric perspective. Oh, you're making it smaller, you're going to use less material. And that's true, right? If you go from sort of the 1 centimeter cube, right, which will give you 1 milliliter, and you go down to sort of the micro scale, right, volume scales is the length cube, so 100 micron cube will give you a 1 nanoliter volume. Okay, so you do get a lot of benefit for the volume, but it's also true that you get tremendous other effects because you have an increased surface area to volume ratio. There's a lot of different physical phenomena that you can take advantage of. And the one that microfluidics has been really known for is this idea of laminar flow, that you don't get the kind of turbulent mixing that we think of, when you pour creamer in your coffee, etc. So these are just aqueous streams with food coloring in them, and they're all flowing together into this larger channel. But because it's a microfluidic environment, you only get diffusive mixing. And so this is where some of these ideas of microgravity, these kind of counter-diffusive properties, can be implemented on the microfluidic and have been implemented on the microfluidic scale. So an advantage of a microfluidic environment is that you do have very reproducible control over how fluids come together, what that mixing or diffusional profile looks like. A disadvantage is that if you wanted to have fast mixing, and we were talking about this, especially with the PEG that came up, right? You have to be very creative in how you can get that sort of fast mixing to occur, if that's what you. All right, so then getting to the idea of microgravity, we've already seen these pictures, but it's the idea of gravity-induced buoyancy effects due to density gradients. And so you can think about this in terms of the Grashof number. I'm in a chemical engineering department, so we love dimensionless numbers. But normally we think of minimizing buoyancy effects by minimizing the gravitational acceleration right here. But you can achieve the same thing, and this scales, again, with the length cubed, by just decreasing the length scale. So I would argue that it should be possible to achieve microgravity-like behavior by just decreasing the length scale of your system. I mean, it's by a factor of 100, but that assumes that you started in the right place, right? So to affect a 10 to the 6th change in gravity, it's the same as doing a 100-fold change in length. And this could be useful, especially in terrestrial applications, or you might be able to take advantage of it to, say, soften some of the impacts of some of these lower frequency jitter types of issues that have been described previously for in-space experiments. Okay, so then that's sort of the overview on microfluidics. Where my lab has really come in is, historically, like if you Google a picture of a microfluidic device, you'll get something that looks like this. So these are going to be, half a centimeter thick. It's a silicon-based elastomer on glass. They work fabulously. But in the context of structural biology, you cannot do X-rays in situ in a device like this. And so if you want to be able to analyze your crystals in place, you really have to think differently about the materials. And so what we've done is we've gone away from these types of silicon-based materials. So here's a plot of transmission factor for 1 angstrom X-rays versus thickness. And things like silicon nitride, PMS, which is this elastomer, quartz, etc., have fairly significant attenuation at about 100 micron thickness. If you go to something like a plastic, however, it doesn't have the heavier atoms in it, so you can get about an order of magnitude decrease in the attenuation for a given thickness. And then, of course, if you can go to thinner and thinner materials, you can push this further. And so this is the area where my lab has really been working on in the last few years. And we got a lot of inspiration from some really nice work that came out of Cornell, out of Soldrunner's lab, where they took a protein crystal, looped it, and then basically saran wrapped it in a graphene sheet. So it was a large area sheet of graphene, and showed that these types of two-dimensional materials can actually serve as a barrier against evaporation. So the crystal that they're showing here didn't have evaporative losses over time during data collection. And also, if you look at the diffraction image, there's basically no background from the material itself, right? So if you can make a device that sort of captures these aspects, then this could be really useful for being able to analyze your crystals without necessarily having to handle them. This is room temperature. They also have frozen these, but you can do it both ways, yeah. Mm-hmm. So graphene is a single atomic layer of sp2 carbon. So it's like a carbon nanotube that's been opened up and run flat. So you can grow these. Graphene is grown by a chemical vapor deposition on copper, and then you can basically back etch the copper away, and so the graphene will be floating on the surface. So you can loop out a crystal and then swipe it through this graphene sheet, and it will wrap around. And getting it right without leaks is probably more of an art than a science, but that's how they did it. Mm-hmm. So this is just the very first report from my group, and these are very large. This is, not fancy production. Everybody could do this if you had some graphene and the right chemicals in your lab. So the first set of devices that we did with this, we have our graphene sheet, and we have a little bit of polymer that we put on the back. So a couple hundred nanometers worth of just a polymethyl methacrylate, just so that you can handle the material, right? Single atom thick things you can't pick up real well. And we just took these graphene sheets and basically sandwiched them around double-sided sticky tape that we'd cut structures into and created microfluidic devices. And so we could do a variety of different geometries. This would be a batch-style device. You could have channels to have counter diffusion. And if you do this, you get really nice crystal growth. So here is an optical micrograph of batch-grown lysozyme crystals. Here's a counter-diffusion picture. And if you notice, there's a bubble right here. Right, so graphene is very, very strong. It actually can serve as a barrier material against evaporation of water. People have talked about using it for hydrogen storage. And so in this case, we had our channel, and my student took protein and precipitate and injected them at the same time in both channels, came together, air was trapped. And that air remained trapped for the next 2-3 weeks while we grew the crystals and then did the analysis. So this is sort of, interesting evidence. And then we did X-ray analysis on these crystals directly. This is at the advanced photon source using a polychromatic source at the BioPharge facility. And the point that I want to make, this is lysozyme, it crystallizes really well. You can get a high quality structure. But what I want to point out is that we have crystals that grew here, and then there's a little one you can't really see right under this support tab. And that tab is about 100 micron thick cyclic olefin copolymer. So this is the same kind of backing material, similar thickness that you'll get in some of the X-ray compatible well plates that are out there. And so we could do a direct comparison of the types of data quality that we could get with just these very thin windows versus the sort of more traditional approach. And if we do that, you can see really clearly the difference in the background from where the thicker plastic is versus the graphene, where the only kind of background scatter that you see is going to be from solvent that's present in the sample. And you can see this just visually, or if you do a radial integration, you can see very clearly the large background signal that's present and what this would do to the signal to noise that you would have for the reflections that overlap with that scatter. Now, I said these were our very first set of devices. We've gone and we've really refined this procedure, and we're working on much more advanced devices now. So our first ones we cut out with a knife. Now we're doing molding against a lithographically defined structure. And so we can do simple structures like wells or channels. And we can go much, much smaller. So this is an array of 6,150 micron wells, if you were going to do a large number of samples. And that's not necessarily what we're talking about here, but the ability to do a very, very high density of samples is something that you can do. So that's just sort of the platform. I wanted to mention one other thing that's really kind of fun. So graphene is a barrier material, right? It'll protect your sample. And it's also conductive. So this begs the question of what could you do if you had an X-ray compatible and optically transparent conductive material in a device, right? Would you want to apply electrodes to, say, do electric field-driven crystallization, right? Where maybe you have electrophoresis that moves the protein along and creates local areas of supersaturation. Would you want to use an electrically triggered, say, valve to drive, move flow around? There's a lot of opportunities here. And from an integration perspective, we could achieve all of these in these types of devices. And then if you go to all the trouble of getting a really, really nice crystal, you never have to handle the crystal. Just take the entire device, mount it at the X-ray beam line, and you're done. And all of the work that I'm showing here, we've done at room temperature. You can do cryo-cooled samples if you want, but these are really nice for room temperature samples. All right, so that's where we're going. We're trying to figure out ways to use microfluidics to kind of address issues that are out there that are kind of at the limits of where the structural biology field is. And there's challenges that we're interested in pursuing from sort of a technological standpoint, right? How can we integrate things? What does it take to translate this type of technology to a broader audience, right? And that means one thing. If I want general labs to use it, it would mean something else. If we wanted to take this and do it on a particular space flight, and how can we couple it with sort of existing automation, whether that's imaging, liquid handling, etc. And then if we can do this, you have the ability to really do a lot of things that are kind of still challenges for traditional structural biology. If you're growing a large number of crystals, you don't have to worry about radiation damage, right? You can just shoot one and move on to the next. Especially if you can grow a large number of identical crystals, right, that all have the same quality. It's not you search through everything in the droplet to find a good one, if they are all that good because they all had reproducible crystallization conditions. The third thing that the graphene is good for, it's a barrier material, so you could potentially have very, very controlled environments on a microfluidic device. Say if you were growing a metalloprotein or something that's redox sensitive to oxygen, if you wanted to have other specific things in there, xenon, etc., the graphene should be able to contain that. And then I want to highlight that these are really good for in situ analysis, for regular diffraction, for things like small angle X-ray scattering, for the continuous diffraction diffuse scattering that you normally wouldn't even see in the background. And then other things with like electric fields, adding materials, etc. So that's basically my talk.
Thanks, Sarah. That's cool. Okay, Ilia's going to talk to us now about salt crystallizations with a stem bent.
Thank you. Good afternoon. I'm Ilia Guzei from University of Wisconsin-Madison, and I will talk to you about something different from proteins. So if Sarah, if you thought you were an outlier, I'm a bigger outlier here. So thank you, Mark, for inviting me to talk about this. And I'm here because in 2014, the International Year of Crystallography, I decided to celebrate by conducting a crystal growing contest among high school students in the state of Wisconsin. So we invited high school students to crystallize simple inorganic materials such as cupric sulfate, KDP, or alum. So we wanted students to learn about crystallization techniques, about solubility, about working in teams. And in fact, there was a lot of peer pressure among high and middle school students. When they form a team of 3 people, they have to take good notes and the lab journals. This is new to them. So it became successful enough, and now we've been doing it for 5 years. We started with high schoolers in 2014, so now we involve middle and high school students, and in 2018 we had over 300 middle and high school students and a number of teachers as well. So we have close to, between 600 and 700 students. This is a map of Wisconsin, middle school participants, high school participants. We are trying to canvass the entire state, and we also invite homeschool children, which is actually difficult because it's very hard to find communities with homeschool kids. I was invited to, Cassis invited us to participate and to explore the possibility of growing crystals in space. And our goals were pretty much the same as for the contest, to learn about solution chemistry, purification, crystallization, but also about microgravity and experiment design and optimization. And in the process, students had to adopt an advanced vocabulary, learn to work in teams, take detailed records, communicate with their teammates, which was not very simple because they lived in different places. So they don't come from the same town. So these are typical crystals that are submitted for our Wisconsin crystal growing contest. Cupric sulfate was chosen because it was the very first compound characterized by single crystal diffraction, and these are crystals of alum. As part of this crystal growing contest, we have an art competition where students submit crystal-inspired art. So these are winners from the middle school and high school. This dress is made with cupric sulfate, and the skirt is made of the inorganic compound solubility table. I thought that was a nice touch. And the drawing by a high schooler shows an astronaut on a planet. The astronaut is probably not drawn to scale, but it's so when we selected 6 people to participate in the space crystallization mission, we had 4 students who won the crystal growing part and 2 students who won the art contest. And Cassis told me, we don't want just the crystal growers. We also want the artists. We want to invite all the students. And so this is our team with 6 students, 3 high and 3 middle school children. And I have to say that nobody is better at outreach than NASA and CASIS. It was a very good experience for us. They started by designing a logo for our mission, and everything on this logo makes sense. The solar panels are blue because we are growing crystals of cupric sulfate. Of course, there's an ISS. We see our planet because we conduct our reference experiments here. The white stars represent KDP, and there is a state of Wisconsin. One thing I didn't know is that you are not allowed to have the US flag on the logo. So that's why we have Wisconsin. And we also have patches, and they glow in the dark. So then, of course, we had to design the experiments itself, and they had to be fairly simple. And we decided to grow crystals by thermal gradient. The plan was to send saturated solutions of our materials to the International Space Station, ask an astronaut to put it in a refrigerator, and due to the difference in solubilities between room temperature and 4 degrees, we would obtain some crystals. The design was fairly simple. We used 35 and 60 milliliter bags, filled them with saturated solutions ahead of time, and we didn't have to worry about any deterioration of our samples. Even if there were a delay with the launch, it wouldn't have mattered because these materials are very stable. So what we did was we charged Teflon bags with solutions and isolated them from the syringe with a stopcock. The idea was that once crystals have grown, an astronaut would open the stopcock to draw the liquid into the syringe from the crystals. That would prevent crystal dissolution upon warm-up. And we had to have a soft container here because on the ground, you can flip the bag over and suck the liquid out. In space, we were unsure how well that would work. But if it's a soft container, you can roll it, you can squeeze it, and you can force the liquid out. And that worked fairly well. We obtained a lot of crystals. So the experience of working with CASIS was much more than just growing crystals. Mark came to Wisconsin twice to talk to our participants about science at the ISS. April met with the students and their parents to tell them how the trip to Florida would go. When the students came to Florida to work in the life science lab of CASIS, so everyone had to wear lab coats, safety glasses, gloves, so everybody worked in teams. April took us to the room where communication with the space station takes place, so that was very appreciated by all participants. And Zoran Radic brought the virtual experience as well. That was an unexpected benefit to the students. These are our basic results. We received large and small bags, and I was surprised how tersely labeled they were, large bag and small bag. So they went into space, they didn't say what was in them, but we did have to have 2 layers of containment because cupric sulfate is a pesticide, so we had to protect the astronauts. The yields from our crystallizations in space were lower than yields on Earth, both for cupric sulfate and for KDP. I'm not sure why, because we conducted experiments in the exact same fashion. The students were introduced to fundamental characterization techniques, such as melting point measurements. I'm showing them here. They're looking at the melting point apparatuses very intently, trying to reproduce literature data, and their results were close to the literature data. I also characterized crystals on an X-ray diffractometer for mosaic spread. The mosaic spread between Earth crystals and space crystals were exactly the same. And we obtained the exact same polymorphs in space as we do on Earth. So there were no surprises. We did Raman spectroscopy, and there are small differences between space and Earth-grown crystals, but these are probably due to experimental conditions and laser polarization. Thermogrametric analysis shows that space crystals desolvate and decompose slightly faster, but everything is within experimental error. So for all practical purposes, crystals behaved in very similarly. Students were introduced to optical microscopy. They used a high-power light microscope to take pictures of the crystals. Visually, it seemed that space-grown crystals had sharper edges, smoother surfaces, fewer imperfections, but it's really hard to tell because this is an inorganic material. The crystals are really good. So talking about differences would not be meaningful. And then, of course, you have some evaporation of the surface. And even though you can see some details, I don't know if that is significant. It did appear that in the bags used at the ISS, we obtained more crystals, probably because once they nucleate, crystals keep growing in the absence of diffusion and sedimentation. On Earth, we seem to obtain fewer crystals. And the impact on students was really significant. The families really made their students to excel. At the Life Sciences Lab, the students worked together. They had to double check each other's results. So they took really good lab notes. You can see that there are a lot of people in the lab, and this was the most well-documented experiment I have ever conducted. Parents and participants took a lot of pictures, so everything was documented. The students became leaders because a couple of them also went. So this was the 2017 team. In 2018, two of the same people won the top prizes. They're participating in the 2018 Wisconsin Space Crystal Mission, and they're leaders. They've become very confident. Now they're telling the teammates how things would work, how they should go about designing the experiment. The students had to give talks at the Kennedy Space Center. So here's the Journey to Mars Pavilion, where they were part of a large group of student participants. They gave posters in the Saturn V Pavilion. I thought it was really cool that they gave posters right there. And they became local celebrities. At least 2 local TV stations interviewed students. And I have to say that the coverage by the media was a little bit off. They would say that crystals would turn blue in space, or that they were proteins, and that was not so. And the final, the conclusion of our trip to Florida was the possibility to see the launch of SpaceX 14. So this is our team that sits here at the observation area. There is a jumbotron that has feed from the station, and there is actually live commentary of what is going on. That was very interesting. And let's see if... So this is what the launch is like.
9, 8, 7, 6, 5, 4, 3, 2, 1.
And because our team was comprised of middle and high school students, we were fortunate enough to have an astronaut record a greeting for our team. So this is Drew Castell.
Hello to the members of the Wisconsin Space Crystal Mission Team, and welcome to the ISS. These high school and middle school students are winners of the annual Wisconsin Crystal Growing Contest, a competition to grow large, high-quality crystals. These crystals have been growing for 7 days in our refrigerator here on the ISS. Good luck with your project.
And I want to conclude by acknowledging a lot of people. We had a lot of support from cases. A lot of people from Wisconsin were involved. We had a number of collaborators. And of course, NASA, cases, and University of Wisconsin-Madison were very instrumental. And thanks to you for your attention.
Okay, I'll invite the speakers to come back up. A diverse set of presentations to ask questions about. Open for questions. Are there any questions? Way in the back.
Of course, you want to use small scale to see how the diffusion process can do the separation of crystals and then scale up from there. And once you scale up, then you have to use a microgravity environment. So I think you're not totally out of the game for that. But my question was, have you ever done ab initio phasing structure determination using that?
So we haven't done it with the graphene devices, but we've done it with a thicker device that gave worse data. So we did selenium sag.
In situ.
Yeah, in situ. So we would.
In situ ab initio.
So we took wedges of 10 degrees on one side and then flipped to the other half. And yeah, we published a paper on that in Lab on a Chip in 2010.
So have you tested? Have you? Well, have you used freezing power to assess the quality of crystals? Comparing quality crystals as an assessment. How would those be different to long channels? And I guess you haven't used it with the graphene.
Yeah, so that's a great question, and we haven't really done a systematic comparison. In the proof of concept work that we did, we compared a single crystal cryogenic approach to what we got on chip, but there were differences in terms of the size of the crystal. It was done at cryo versus at room temperature, so it wasn't really an apples to apples comparison. But that would be a good thing to do to actually use that as a metric.
I have another question for you. So you showed a slide. We go back to the panel D in the upper right-hand corner. Had a lot of green color. You were showing the growth of lysosine crystals in all these cells. Slide about that. Okay. It looked like there were 4 crystals growing, all with identical orientations, all nucleating on the side walls. So, like you're looking down the tetragonal axis in every single one. If you imply that the epitaxial nucleation set the orientation of those crystals, so you've got an found pretty good epitaxial nuclei, so whatever the side walls are, because they give you oriented nuclei.
No, that's a good question. We didn't look at the orientation.
Look again.
But yeah, no, we can't. We can go back and look at it because we did full data sets from them. But yeah, no, I think you're correct. And I know what the surface treatment was. Whether or not it would work in all things is a separate question.
Questions for Leah. With the recommendation outreach program, I was wondering, have you ever followed up on the students on the academic impact of the activities?
So the question is whether I have followed up on the academic achievements of the students.
Yeah, any assessment criteria, test scores, or anything, or have you
done it long enough where you can actually track these students and look at their success impacts on the you fund their participation with your crystallization?
So a part of this contest, and this is why I wanted to do it in Wisconsin, is that at the end of the contest, we invite all participants to the chemistry department. They listen to 2 hours of lectures, and then they tour our campus, and they tour our department. They see teaching labs, research labs, they talk to graduate students, they see the X-ray lab, the glass blowing shop. The idea is to inspire students to go into sciences, to go to college. I don't have any statistics to tell you, but all my evidence is anecdotal. That some students now want to become chemists. And again, we are talking about students who are a few years away from college.
Also, you could show a convincing case that a student that was not otherwise going to a STEM area are now going into it because of what you've done.
This is a very good suggestion.
Yeah, a further comment along those lines. We ran an educational outreach program about 20 years ago. Jenkins was involved, and we reached something like 6,000 to 8,000 students who were preparing samples for us to fly into space. And we did a little bit of tracking on those students. And there clearly was a positive effect. Many of those students went on to very fine universities. And many of them really redirected their careers in science as a consequence of those experiences. So I give you all the encouragement in the world to pursue this.
Thank you. Yes, I'm not surprised with your results. I know that I wrote these students letters of recommendations, and at least one of them is going to the space camp in Huntsville. So, yeah, I can do that.
It's interesting to hear how the male-female aspect of it. Because I know when I first started out, there was mostly, we were talking about this a while ago, mostly males in my engineering classes. I have a daughter that's switching off into engineering. That percentage is really increasing a lot. So do you observe anything from that kind of angle to see if the girls are really positive about it? And I'm hoping you say yes.
So in the Wisconsin contest itself, there are more girls than boys. In the 2017 team, there were 4 girls, 2 boys. In the 2018, there were 7 people, 1 boy. So for us, it's all female.
Tim?
I need to know where you got those little bags.
The large bag and the small bag?
Yeah, the large bag and the small bag. It was all bought commercial. So
it's easily adaptable for calculated analysis. Doing the same. That would be a wonderful change.
The Ivy bag was the original idea. We couldn't fly those. We had to go with these Teflon bags.
Those are the Teflon bags.
I looked at it.
Teflon bags.
Okay. We actually get them designed to order. And probably like a dozen generations of bacteria in one space set. I can get it.
Joe?
Not to monopolize this. I was just wondering, what is the criteria of participating in the program?
So we select the best crystals and the best artworks. There was
How do you select the participants?
for the Wisconsin or the space program.
For the space program.
Okay, so the winners of the Wisconsin contest become participants in the Wisconsin Space Crystal Mission. So whoever wins the contest gets to crystallize materials at the ISS.
So these are good students to start out with.
Good crystal growers.
But the reason I'm asking is that I always wondered, you didn't get the top students. You got not the A's and B's, but the C students, and get them involved with this to see how much difference is and how much impact you make.
Well, that would be something to do in the future.
participate on the state level? And do you see them like getting excited? Because that might get to the question of the lower performing C students or whatever. Like if they get more and more excited as they go on or something like that.
So yes, of course, every year the same people participate. And I can tell you that in these 5 years, the quality of crystals has improved. Because the teachers know how to grow crystals better.
They see if you fly more than once.
Yeah. Tim.
Back to business. The RFP that's coming out, that is going to be like the little process to add on to normal crystallization. So we're going to allow microgravity crystal growth for crystallography. That's the point. Right. So you said that the upfront cost would come from the people.
From the PI, right.
But that would be just a different protein area.
Right.
But to get stuff to you guys, you would fly. Mail them to you, fly them that way.
Right. So you would work with one of the implementation partners to come up with that side of the plan.
And we don't the cost of that.
We pay for that.
Apply a cost to that.
Yeah. So you get that cost into the final proposal, and that part of the proposals will be evaluated on the total cost. There's right now it's there may be up to $1 million to cover those costs. So that they'll be primarily ranked on their scientific and earth benefit, but there will also be cost consideration as part of the proposal.
And this is separate from the real plan of the neutron.
That's correct. Yep. So we've got a lot of different things going on, right? Yeah. So I think that it's an area that people are interested in, and we're trying to work with the community to find out the best way to promote it and give you guys access to it, and starting to transition towards at least recovering your side of the equation.
You mentioned that it's all eventually hope to get the investigators to pay the implementation problems. What's the price tag?
Yeah, so it's definitely going to be something we want to bring up in the breakout sessions, and I think it's a question going forward. Is it in an open market, what would that price tag be? I think that if it was like a high throughput center, you drive down costs because of scales of efficiency. Obviously, we're limited to a number of light opportunities, so we don't have like the same cost setup as that, and so the implementation partners are limited on driving their costs down there. But it's the attractive thing about getting set hardware that we know works, and maybe those costs can start, at least the development costs start getting driven down, so that it becomes reasonable that people might see the advantage of paying for it. So that's a question that we have for the community. Are we going to get to that point? And if we don't, then do we need to move to a model much closer to what Joe was describing, or even closer to the real-time PCG that Craig talked about? But it's we have focus groups that put together, and we get somebody else to fund it, and we just do it that way. So I think those are the questions you're asking. You can ask the implementation partners their costs.
Yeah. Well, just to put it in perspective, the standard RO1 grant is about $250 per year.
Right.
So if it gets up to tens of K, then that's a significant impact.
Right. Yep.
So do you think it will be tens of K or more, or less than that, amenable to the whole community?
Yeah, I think for the academics, I mean, my personal opinion, I think that it needs to get down to that level for it to be a viable option. And what I'm hearing from the community is there's maybe some proteins that might warrant a larger cost, but if we put it into a drug discovery paradigm, like in a commercial paradigm where you need a 6-month turnaround, spending $500,000 probably isn't going to cut it in 2 years. But it's a high value target that needs that. I think that there could be justification for that. But we're looking for the community to drive that. We don't want to limit that. We want to see if it might be
Chris?
This is probably for Mark today. I think there's a lot of attention that gets put on trying to make a presentation in space. But I'm curious if there's any studies into that, how you can better handle crystals once they come off Dragon and are sort of being transferred to our laboratory. So that could be a really big sort of stumbling block to our analysis.
Yeah, I agree.
You want to repeat it?
Oh, okay, sorry. The question was, well, we hear a lot of talk about enabling crystallization on station. Is there any thought into handling the return of the crystals from station? I think one of the things I was surprised about when I started that thesis, knowing nothing about space, is that Dragon capsule returns in the Pacific, and there's not really any lab facilities over on the West Coast to process this. So I mean, I think that that's something we're going to definitely take back from our side. I think we hear it on some of the other types of payloads that come through is the necessity to do that. It also comes down to there's only so many launches a year, so there's expect to justify having a presence there to process that. And hopefully with the CS virtual service exclusive too, I always get confused on the NASA acronyms, but some of those capabilities will allow us to land much like the setup delivery samples. So that may be really attractive to this community, and that capability comes available.
Right, so that would be Sierra Nevada developing green chasers, which will land on a runway, so it'll be much less central return. But you're absolutely right. There tends to be, there's such an allure about thinking about the spaceflight aspect of the experiment. It's the whole chain reaction. If you throw a wonderful crystal and then slam it in the wrong place so it can splashdown, it's worth or if you can transport, exposed to high temperature. So I think that's what the implementers, there's not a specific NASA effort looking at that. I think that's something that all the implementers are motivated to refine because it affects the success rate and that's going to affect their business.
I was just curious of the people that are here that have retrieved crystals. How did you do it? Did you go and go to the air? I know, Joe, you went to the airport, right?
So I can tell you, I didn't have time to really talk about it in detail, but I think one of the biggest challenges that we face, not only for me, but for other people, is what we talked about before, was getting secretron time or getting neutron time prompted after you get the crystal.
No, I'm actually asking, can you tell us how you retrieved the crystal? Logistically, what did you do to get them from the ocean?
We went to a pilot airport, and there was a carrier that came from the ocean to that airport. And after that, once you sign off on it, you're on your own. So for me, we went into a hotel late that afternoon and took a plane out of LAX. And then that went through different layovers. And so it actually, it was in the cabinet, carried on, but I was actually holding it. And before takeoff, they were telling me to let go, so I turned it up so that way even it won't absorb the vibration. So there is a lot of personal effort behind it. You're right, I agree with you. The post collection of it, so many things can go wrong as part of this.
I'll tell you what we do. In the shuttle days, when they declare the orbit burn, we either go into KSC or drive. Now called. So we would reposition we would charter 2 aircraft. So with one, in case the orbit burned, send it to a drive. And that was the worst case scenario, way out in the desert. So we would take the lab, that we would take our portable lab, all of our equipment that we would take to KSC to do the sample loading. We would take that with us post-land. And we'd have a system that was a human operation oscillation system. We have the hardware, we set it in there. If it required temperature control, we'd have battery packs. And so if it went to drive, we would have the charter aircraft there with 2 technicians to get it. We'll go wherever the PI wants us to go. So the planning we did on the front end, we did on the back end too.
Okay. One more question.
enthusiasm meter, where is the needle for NASA in terms of protein crystal growth in general nowadays? And I'm asking that because a lot of the calls for NASA research may coincide with things that we can leverage and work together with cases and some of your calls. And I was wondering, what is the outlook now on protein crystal growth? If you write that on a proposal, will people roll their eyes at NASA panels, or will they still?
Yeah, so I think, Joe, in the near term, don't expect any solicitations in the protein crystal growth realm. This RT-PCR effort is really capitalizing on this capability that we realized with the activity time that we have and the possibility of really eliminating some of the decrements that we had or some limitations before. If, however, these things really make a difference and the cases usage really picks up, and there seem to be some important things that can be tackled, then I think we will step up. So one thing that has really been a mindset change in the last couple of years, and really most dramatically this year with the President's budget request going out, the emphasis on commercialization space, is back when Eddie and I were at Marshall, and Dan before that, we didn't think of it explicitly in these terms, not consciously, but we owned the domain of doing in the United States, doing research in it. Now, if you wanted to do PCG, you had to come through NASA. We had the launch field. We had the orbiting platform. We had the hardware. We issued the grants. And as a matter of policy, where we're trying to go is, especially for Ilia, is get to more of a commercial type of world where costs can come down, and when you write a proposal to NSF or NIH, in your budget section, you're allocating something, 5K, whatever it is, for the spaceflight opportunity. And just like using any facility, there's a track record that warrants that cost. If you're a new panel, is going to find it reasonable, and that's where you go. That's the direction that we're heading. As opposed to, in former decades, putting a lot of investment in crystal growth studies for their own sake. Right now, as a matter of policy, that's not our direction. But if we do identify practical problems that require, or NASA is the right entity to bring together something like a science definition team to tackle it, we'll do that. But don't expect anytime soon a call for the fundamental protein crystal growth studies, or really in the old days we had the guest investigator. That's really, that niche is really filled by cases.
Okay, thank you. We're going to take a short break.